Okay, here for Class 8, we're going to do some example problems to get us as a review for Exam 1. Some of these problems might be duplicated in the practice problems that are in the exam prep folder on Blackboard. But, you know, I think that it's good to have lots of different resources and lots of examples. So combining what we have in the class examples, the homework and the homework solutions that you'll see, and then these exam preps, and then there's another whole set of exam prep problems, and I will post the solutions to all of them a little bit before the exam so that you'll have a chance to do the work. But watching someone solve problems isn't a good exam preparation strategy. You really need to take a blank piece of paper, look at the problem, and then start solving it yourself. And even if you think that you're wrong, just keep going all the way to the finish of the problem, and then, only then, look at the solution and look at this solution video, for instance, and see where you went wrong, and then try another problem. Because the only way that you could be prepared for an exam where you're asked to solve a problem is to practice solving problems, right? So not watching someone else solve problems. It doesn't help. It really doesn't. Unless there was the exact same problem, then you're just memorizing what you're supposed to do. Because there's always some little different set of circumstances, and as soon as you start seeing a problem that you've never had before, you've never seen before, you're going to get all tripped up on an exam. So what you need to do is actually practice that thing where you try to figure out the solution. But anyway, I could say that until I'm blue in the face. And I probably have, and I probably will keep on doing it. But anyway, wanted to give you that advice. It's up to you. All right, so the solid steel cantilever bar that we're seeing here, so this is a door handle problem, supports a load of 1 kilonewton in the X direction, 1 kilonewton in the Y direction, and 1 kilonewton in the Z direction, and has a torque of 100 newton meters applied to it. The shaft is 200 millimeters long and has 25 millimeters diameter. We want to calculate the combined stresses at element A and label them on the provided stress element. And do not neglect transverse shear. I keep saying this, I think, each time I do this, like, I really should have mixed these up a little bit so that they don't go in the same directions, so you have experience doing them in different directions. But I keep seeming to forget to do that, so maybe I'll do it next semester. Anyway, so there's the problem right there, and because we're trying to find it at element A, we only need to do one free body diagram. See, like on an exam, we would only make you do one free body diagram. Maybe. I'll try to simplify problems in a way and make them shorter and that kind of thing. But you got to realize which one you have to do. And so if it's going to be at A is where the stress is going to be, we want to do our creepy little eye looking at it from the side. So we want to have it in the XY direction. So we'll do our FBD. And you'll note we have this one here, 1 kilonewton. This is Fx acting on it. And we have 1 kilonewton acting downwards on it. Our reactions are going to be right here. We're going to have an Ry. Oh, by the way, I should have gone X and Y right there to show that. And we're going to have a reaction coming this direction with our Rx. Right, do that right. And then in terms of a moment, this is going downwards, right, going clockwise. So this better go counterclockwise. So there you go. There's your M, and I'd call it MZ, right? And so simple thing right here. Okay, this is also 0.2 meters long, right? So they said 200 millimeters, so it's 0.2. So the sum of the moments, easy enough. About the z-axis equals 0. We see that we have a negative 1,000 newtons going against 0.2 meters. And here is the plus mz, and then equals 0. So the reaction moment is equal to 200 Newton meters. Not really all that difficult. Some geometry I might wanted to have gotten out of the way. It said it was 25 millimeters. If I find I need the area, which is pi over 4. So the diameter is 0.025, 25 millimeters, or 0.025 meters, and I get 4.909 e minus 4 meters squared. I is pi over 64. 0.025 fourth, or 1.917 e minus 8 meters fourth. And J is just 2 times I, because it's a circle, which ends up being 3.835 e minus 8 meters fourth. All right, so there's the geometry. Here's the loads. They gave us some of the other stuff. So now we just go down one at a time for stress. We start with axial. We say, well, not that. And I'll say axial. F over A. And that's going to be that 1,000 divided by that right there, right? So 1,000 divided by 4.909 e minus 4, and we end up with 2.037 E6 newtons per meter squared, which is the same as 2.037. I'm looking at this, and it's weird. I show that as being compression, but on my other one, I show it as tension. So this is definitely, that just jumped at me. That's going to be compression, right? It's pushing down in there. Interesting. So let me fix that as numbers down here below. And, okay, so there's stress right there. And for bending, we have bend. It's going to be equal to MC over I, right? Going to have that memorized. And that's going to be 200 Newton meters. The C is going to be 0.025 divided by 2. The I, 1.917 E minus 8. And we're left with 130.4 megapascals. And in this arrangement right here, we see that that's going to cause tension at A. Next, I'm going to go torsion. Tau, and I'm going to go TORQ, is going to be TR over J. We were given that they are applying 100, 100 Newton meters, and 0.025 divided by 2 is the radius to that outside fiber where A is located. And we have 3.835 E minus 8 is going to be our moment of inertia, our polar moment of inertia. And so we end up with a 32.59 megapascals. Right there, I divided by 1,000,000 before I started writing the thing down. All right, let me see. Okay, and then now last we have transverse. So I got tau, tran. That's going to be, now this is a circle, so we know that the maximum is going to be 4/3 V over A. So I get 4/3. But what's the V that's going to cause transverse shear in this arrangement? And is it going to be Fy or is it going to be Fz? Well, they're both equal to 1,000, so it didn't. We wouldn't be caught if we accidentally picked Fy. But it's going to be Fz because it's, remember, this transverse shear maximum is to the side of where the force is going. So we're we're going to go ahead and put 1,000 in there, but make sure that we were being specific that it was FZ that was doing the thing right there. So we go 4.909 E minus 4, and we get all of 2.716 megapascals. Now here we're going to have to make a decision as to whether these guys agree with each other or whether they're going in different directions, right? And sometimes what's really going to help us with that is going to, instead of the free body diagram, look at the equivalent loads diagram, and that's a pretty easy one here that's going on right there. Like we'll just do it as symbols. Right, so there's going to be A, right? So there's the top view of A, but here's where A is after it's been exposed, right? And let me double check. Yeah, here's the Z and here's the Y right there, right? So there's the X, and it's kind of funny. I don't know why I have. I'll put it the right way. Okay, so here's the FX. I don't think on my diagram I am actually showing which way my torque is going. It's weird. I don't know where this diagram came from, but this is the one that's in the notes. It needs to have that T be placed onto there. So I need to fix this diagram. I need to probably just replace this whole problem here as the example, but I'll do this one and then I'll keep this video, but maybe I'll add another one soon enough. But anyway, there's the F of X going on right there. We take a look, and here's the FZ, and right here is the FY, and right there is the torque that's taking place. And in terms of the moment, here's the moment about Z would be causing that way, and if we wanted to care, here's what the moment about Y was going to be. But that moment of Y would only affect that little guy that's actually marked as B over here, but we only care about A. So when taking a look at our little a little stress thing for A, I'm probably going to look down onto the thing, and probably in that direction right there. So X is going to be aligned with that, and Z is going to be coming downwards if that's the way that I choose to put onto the thing. So I'm going to have tension due to my bending, but compression due to my axial. Now, when it comes to torsion, torsion's going across this face. You see how it's coming this way right here? So it's going across this face. So it's going downwards right there. So I'll say that's torque. And then also, this FZ is the one that's causing a maximum to the outside. So I also have tau tran coming right down that direction. So, and of course, all the other guys are going to be, pointing out in this direction right here. But the long and the short of it is the sigma x right there is going to be 130.4 bending minus 2.037 axial, because the axial as drawn was what was I saying? Yeah, as drawn was a compression. So 2.037 minus, so I get 128.4 megapascals in tension, because that's larger than that. And then the tau xy, these two are in agreement, so we're just going to add them together of a 32.59 plus my 2.716. And if I did that right, I get 35.31 megapascals. So my answer, if I was being asked to do it, asked to diagram this, would look like that. And I would definitely be in this condition. Now, there'd be other conditions where I'm not going to care. I'm not going to care about what direction the shear is going to go. But here I want you to show that you would know, if you had to, what direction the thing is going to go. So here's your 35.3. Only need 3 sig figs in the answer. 128 megapascals. Only need 3 sig figs in the answer, and you don't need to have tension or compression on this one because that arrow shows. So that would be what the correct solution would be to what's being asked in this example problem. So that's it for this problem. I didn't ask you to do the Mohr circle. I probably asked that as part of another problem, although it's, you know, kind of a reasonable thing to work through and find this Mohr circle to do a complete problem. So I'll make another video for the next example.